Guys, do you know which is the biggest thing in the world? If you say India, no. If you say the Asia, no. If you say the Earth, then also no. The Jupiter, Sun, our galaxy, the Milky Way, everything is a no. The biggest thing in the world is yes, the universe. Do you know how the universe looks like? If you compare to our galaxy, it will look so huge you cannot imagine. See, now I will show you how it will look like. It would look like this. See, this is how the universe would look like. And here, we are here, in this place. Now you got it? How big the universe is compared to our galaxy? Yes, you got it right. Today, we are learning about the universe. The universe is all of space and time and their contents, including planets, stars, galaxies, and all other forms of matter and energy. While the spatial size of the entire universe is unknown, it is possible to measure the size of the observable universe, which is currently estimated to be 93 billion light years in diameter. In various multiverse hypotheses, a universe is one of many casually disconnected constituent parts of a larger multiverse, which itself comprises all of space and time and its contents. As a consequence, the universe and the multiverse are synonymous in such theories. And yes, the meaning of light year is an year for the speed of light. And if you compare the time from Earth to the Moon in light speed, it can go in 0.56 seconds. Now imagine, if it is 93 billion light years in diameter, how huge can be the universe? Further observations improvement led to the realization that the Sun is one of hundreds of billions of stars in the Milky Way, which is one of at least hundreds of billions of galaxies in the universe. Many of the stars in our galaxy have planets. At the largest scale, galaxies are distributed uniformly and the same in all directions, meaning that the universe has neither an edge nor a center. At smaller scales, galaxies are distributed in clusters and superclusters, which form immense filaments and voids in space, creating a vast foam-like structure. Discoveries in the early 20th century have suggested that the universe had a beginning and that space has been expanded since then and is currently still expanding at an increasing rate. Like in the summer holidays, how our stomach expands. The Big Bang Theory is the prevailing cosmological description of the development of the universe. According to estimation of this theory, space and time emerged together is equal to 13.799 plus 0.021 billion years ago. And the energy and matter initially present have become less dense as the universe expanded. After an initial accelerated expansion called the inflationary epoch at around 10-32 seconds and the suppression of the four known fundamental forces, the universe gradually cooled and continued to expand, allowing the first subatomic particles and simple atoms to form. Dark matter gradually gathered, forming a foam-like structure of filaments and voids under the influence of gravity. Giant clouds of hydrogen and helium were gradually drawn to the places where dark matter was most dense, forming the first galaxies, stars, and everything else seen today. It is possible to see objects that are now further away than 13.799 billion light years because space itself has expanded and it is still expanding today. This means that objects which are now up to 46.5 billion light years away can still be seen in their distant past because in the past, when their light was emitted, they were much closer to Earth. From studying the movement of galaxies, it has been discovered that the universe contains much more matter than this accounted for by visible objects, stars, galaxies, nebulas, and interstellar gas. This unseen matter is known as dark matter. Dark means that there is a wide range of strong indirect evidence that it exists, but we have not yet decided it directly. The ACDM model is the most widely accepted model of our universe. It suggests that about 69.2% and the sign which I don't know plus 1.2% in 2015 of the mass and energy is the universe is a cosmological constant. or in extensions to ACDM, other forms of dark energy such as scalar field, which is responsible for the current expansion of space, and about 25.8% and 1.1% according to 2017 is dark matter. Ordinary baryonic matter is therefore only 4.84% and 0.1% according to 2015, as I am telling it again and again, so please understand, of the physical universe. Stars, planets and visible gaseous clouds only form about 6% of ordinary matter, or about 0.29% of the entire universe. The prevailing model for the evolution of the universe is the Big Bang theory. The Big Bang model states that the earliest state of the universe was an extremely hot and dense one, and that the universe subsequently expanded and cooled. The model is based on general relativity and on simplifying assumptions such as homogeneity and isotropy of space. A version of the model with a cosmological constant lambda and cold dark matter, known as the lambda CDM model, is the simplest model that provides a reasonably good account of various observations about the universe. The Big Bang model accounts for observations such as the correlation of distance and redshift of galaxies, the ratio of the number of hydrogen to helium atoms, and the microwave radiation background. The initial hot, dense state is called the Planck epoch, a brief period extending from time 0 to 1 Planck time unit of approximately 1043 seconds. During the Planck epoch, all types of matter and all types of energy were concentrated into a dense state, and gravity, currently the weakest by far of the four known forces, is believed to have been as strong as the other fundamental forces, and all the forces may have been unified. Since the Planck epoch, space has been expanding to its present scale with a very short but intense period of cosmic inflation believed to have occurred within the first 30 seconds. This was a kind of expansion different from those we can see around us today. Objects in space did not physically move, instead the metric that defines space itself changed. Although objects in space-time cannot move faster than the speed of light, this limitation does not apply to the metric governing space-time itself. This initial period of inflation is believed to explain why space appears to be very flat and much larger than light could travel since the start of the universe. Within the first fraction of a second of the universe's existence, the four fundamental forces had separated. As the universe continued to cool down from its inconceivably hot state, various types of subatomic particles were able to form in short periods of time, known as the quark epoch, the hadron epoch, and the lepton epoch. Together, these epochs encompassed less than 10 seconds of time following the Big Bang. These elementary particles associated stably into every larger combinations, including stable protons and neutrons, which then form more complex atomic nuclei through nuclear fusion. This process, known as Big Bang nucleosynthesis, only lasted for about 17 minutes and ended about 20 minutes after the Big Bang, so only the fastest and simplest reactions occurred. About 25% of the protons and all the neutrons in the universe by mass were converted to helium with small amounts of deuterium, a form of hydrogen, and traces of lithium. Any other element was only formed in very tiny quantities. The other 75% of the protons remained unaffected as hydrogen nuclei. After nucleosynthesis ended, the universe entered a period known as the photon epoch. During this period, the universe was still far too hot for matter to form neutral atoms, so it contained a hot, dense, foggy plasma of negatively charged electrons, neutral neutrinos, and positive nuclei. After about 377,000 years, which is in Indian units 3,77,000 years, the universe had cooled enough that plasma neutral atoms are transparent to many wavelengths of light, so for the first time the universe also became transparent. The photons released decoupled when these atoms formed can still be seen today, the form of the cosmic microwave background (CMB). As the universe expands, the energy density of electromagnetic radiation decreases more quickly than does that of matter because the energy of a photon decreases with its wavelength. At around 47,000 years, the energy density of matter became larger than that of photons and neutrinos and began to dominate the large-scale behavior of the universe. This marked the end of the radiation dominated era and the start of the matter dominated era. In the earliest stages of the universe, tiny fluctuations within the universe's density led to concentrations of dark matter gradually forming. Ordinary matter, attracted to these by gravity, formed large gas clouds and eventually stars and galaxies. Where the dark matter was most dense and voids where it was least dense. After around 100 to 300 million years, the first stars formed, known as population 3 stars. These were probably very massive, luminous, non-metallic and short-lived. They were responsible for the gradual reionization of the universe between about 200 to 500 million years and 1 billion years, and also for seeding the universe with elements heavier than helium through stellar nucleosynthesis. The universe also contains a mysterious energy, possibly a scalar field called dark energy, the density of which does not change over time. After about 9.8 billion years, the universe had expanded sufficiently so that the density of matter was less than the density of dark energy, marking the beginning of the present dark energy dominated era. In this era, the expansion of the universe is accelerating due to dark energy. Today, it's only this much, and don't think that the universe is only this much. It's more and more and more information about this, but I gave you some brief information which you can understand and also I can understand. Thank you. I hope you enjoyed the video.